I'm not sure where this exactly fits in the hazards section, but we do talk about a gas plume, and actually, it's actually a source of possible science, and we'll talk about that a little bit as we get going here. And really, let me do a setup here. As we know, these landers have these gas plumes, and the gas actually impregnates the surface and it absorbs, and that surface deposit will later outgas as a function of time later on in the mission as the surface warms up. And the person who really modeled this and really kind of sets the tone here is Prabhathi Prem in her 2020 paper. And she looked at a Chang'e 3 class lander and found some papers that indicated that about 30% of the plume gas deposit should form water. She then looked at the outgassing as a function of time using Monte Carlo Exosphere model. And one of the big things she found is that for a lander up near about 70 degrees latitude, a lot of that water ends up in the cold trap. So about 10% of the water ends up in the nearby cold trap, and actually even up to 1% ends up in the cold trap in the other hemisphere. So there are global consequences for these landings. Well, what we did in this study is we used some of Prabhathi's results and sort of built upon those. In particular, what she found as one of her results is that for this Chang'e 3 size lander, there's a 2 kilometer by 2 kilometer region where you have water built up on the surface greater than a single layer. You have multi-layers of water. And what we did to model that is we considered a water that was at a surface density that results in essence 9 layers above the surface. So what we assumed is that about 90% of the water is in water-water interactions with a desorption activation energy of about 0.45, but the remaining 10% are in more complex desorption situations, binding energy situations with the regolith. And what we did is, and of course, water isn't really nine layers like that. Of course, it all spreads out. And we considered other variations on this model, and we'll talk about that as we get going near the end of the talk. But what we did is we assumed that 90% of the water were in water-water interactions at lower binding energies. And then 10% were in these water regolith interactions. We then looked at the outgassing of this water deposit over time. Rather than doing global, we actually looked at the local exosphere at and near the lander, because in fact, these astrobotic lander is going to have 3 mass specs. One of them actually will have a vertical sensing direction to look at exospheric water. What we also did is we didn't assume one binding energy, but instead we assumed a distribution of desorption activation energies, sort of like what you would get in a real complex situation. We also didn't use a Monte Carlo method. We instead used analytical formalism from Barry et al. And just to give you an example of the kinds of distributions that we're talking about, rather than picking one binding energy, we actually really almost we could model up to a continuum of binding energies. And in this particular model, this is the most complex model we developed. We included Gaussians to make up the various activation energy states, to describe the various activation energy states. And so for water and Mari regolith, water-Mari soil interactions, we assumed that the values were relatively low, consistent with Michael Poston's 2015 paper, where temperature programmed desorption found that Mari samples don't have a lot of binding energies or desorption activation energies up at high values. We could also add another distribution, a Gaussian type distribution that represents the binding energies that you would have in highland samples, where about 10% of the water regolith interactions, or in this model, 91% of the population would be on binding energies up around 0.7 EV. And finally, we could add to the model Amanda Hendricks's LAMPS distribution, where you where she found that the water desorption activation energy could be, inferred that could be up near 1.3 eV. And so we could sort of mix and match these Gaussians, and then we examined how this complex surface with this complex water binding energy to the surface in other waters, how that would desorb over time. So the first thing we calculated was the surface water density as a function of time. That's shown here. I show the profile that you would get if you had a Mare-like sample with low binding energy with values below 0.6 eV. And then one if you had a highland sample, which had a population of higher binding sites. And then the LAMP example where you have sites really up at high binding energies, a smaller fraction, but up at higher binding energies. And what you find is the water levels drop by a factor of 10 within a few hours. And actually what happens is if you had a Mare-like sample, Mare-like regolith near the lander, the water would keep outgassing to very low values. In fact, you get about a factor of 10 to the 10 drop in water retention within a day. But if you have regolith that has these higher activation energies, higher binding energies for the water, you then get a delay in the surface emission for up to a day or two after landing. Right, and in fact, in the LAMP case, the surface never really gives up all of it. The deposit never really gives up all of its water in the course of the mission. This, of course, gives rise to, you can calculate what the exospheric density would be. And again, in the Mare case, the exospheric density drops within a day. There's no more local water. But in these cases where you have the higher binding energy, you can have what we call a lingering exosphere, where you'll still get relatively high water values, about 1 per cc in the exosphere for a few days after landing. This would also mean that the water influx into an opening like you'd have in a mass spectrometer, you can calculate that, which is really what we're trying to do here, is make predictions for what astrobiotic PITMIS mass spectrometer would see. You would see that drops off, but again, over past a day or so, if you have water on these tighter binding sites, they would desorb later on in the mission. One thing you have to contend with is lander contamination, and in a recent Icarus paper, we were dealing with that. Basically, in order to see down to 1 water molecule per cc into a mass spec, it actually places an outgassing requirement on the astrobiotics, or any lander for that matter, of about 2 times 10 to the minus 11 grams per centimeter squared per second. So on future lander missions, we probably want to write in these kind of lander contamination requirements. And again, this is water outgassing from the lander that goes through collisions with the exosphere and with other waters. And this water contaminates and really keeps us from resolving the water from the landing Plume deposit nearby, and even the global exospheric water. So we also asked the question, what would happen if a greater percentage of these waters were on, rather than being in water binding situations, were on water regolith interactions? And so if you increase that percentage, particularly if they had a higher percentage on binding energies that were relatively high, you can see that you can get maybe another factor of 10 to 100 higher in the lingering exosphere late, a day or two after the mission, after landing. I'm sorry, and again, these are 1 hour, 1 day, and 10 days after landing. So to conclude, well, this model shows that you could possibly use a mass spec to infer the desorption activation energy by simply inverting what we were doing here in this sort of forward modeling study. In some sense, you're doing an in situ temperature programmed desorption study. And again, if you look at the paper, we have this paper that came out in Icarus earlier this year that also includes calculations of landing at other local times, and some other regolith water regolith binding energy scenarios. So anyway, that's it right there, whole thing.